so let's talk about, I will tell you this is my specialty, okay? So this is nearest and dearest to my heart of the things that I do. I love teaching teachers, but I also like creating astronomy visualizations. So I like calling this talk Truth and Beauty in Astronomy Visualizations. Hello. Okay, there's just a little conversation. There we go. That's room. All right, so we have the Hubble Space Telescope. And it is our job in the office, our charge in the Office of Public Outreach to get the science of Hubble out to the public. All right, and trying to get ideas about it. And we have a great advantage in astronomy in that we got gorgeous images, right? And with these gorgeous images, we can attract people's attention just with the image, and we pull you into the image, and then we can start telling you the science about it. Okay? And so we have a beautiful advantage that other sciences don't have. We got pretty pictures, okay? You don't see too many electron microscope images on the front page of the New York Times. We do get the front page of the New York Times, okay? So what we try to do, however, is in my group, I'm the lead of a group that does astronomy visualizations, trying to take these images and turn them into movies. So we want to take the science data, all right, and we want to present it through animations, computer-based animations that bring you into it. All right. Our biggest challenge is not actually the Hubble images. Our biggest challenge is that you guys are used to seeing things like this. This is an image. This is an advertising poster for the movie Avatar, and it's one of my favorite things to show because it is almost entirely faked. All right, it's almost entirely computer graphics. You know that there are no blue Na'vi people. All right, that's just computer graphics. There are no flying dragon things like this. That's also computer graphics. There are no helicopters that have rotors like that, okay? That's computer graphics. There are no floating islands like this. All right, take a look at that picture. Almost everything in that picture, apart from the background plate, which I'm told was either shot in Hawaii or New Zealand, almost everything else is faked. And but does it matter? This is a fantasy movie, okay? But it is believable, okay? And that shows you the state of computer graphics in Hollywood these days, is they can make this totally fantasy world believable. And unfortunately, when we're trying to create scientific graphics to get out to the public, this is the standard by which you get used to, and not a standard we could meet, but a standard by which a relative standard to which we will be judged. All right, so this is our entire wonderful team that creates our 3D graphics things. Myself, Greg Bacon, 3D artist doing Maya, Lisa Furtari, also another 2D artist doing Photoshop type stuff, and you met Zolt on Monday. What we are holding right there is a piece of IMAX film. That's actually from the IMAX short film we made in 2003. And that is the actual scale of the IMAX film print. Okay? So, given that, I will show you how we try to combat all these wonderful things, your preconceptions of the ability to easily do computer graphics, because 4 people wouldn't even serve lunch to the computer graphic teams that work on the movies you see. Just go watch the latest, there's got to be an Avengers type movie out or something like that. Or Thor, one of those, right? Go watch the latest one of Age of Ultron, right? Is out there. Because I remember my wife taking me to that. She loves those movies. Watch the ending sequence of all the computer graphic artists that are working on those things. There are hundreds and hundreds of computer graphic artists working on those films. All right, we got 4. So here's what we're trying to do. All right, so let's start with Night of 1,000 Stars. All right, what we're going to talk about is trying to visualize stars. And we're going to go back to the Orion constellation of Orion. And the problem with talking about constellations is that you draw in those constellation lines, all right, and it gives you an idea of, okay, well, there are the constellations, and we plotted them, and they put them on a plane, right? Moreover, you can draw in the figure of Orion. This is Johannes Hevelius's drawing of Orion from a couple hundred years ago. And you get the idea of a picture on the night sky, And it brings out a misconception that we've found, is that people, even though they know the stars are at three-dimensional distances, tend to think of them, when you draw them like this, that they're all at the same distance. That stars are all at uniform distances away from you, because you're representing it on a plane, and that's just naturally everything's at the same distance. Orion the Hunter is battling Taurus the Bull up here, aided by his hunting dog Canis Major and also Canis Minor up there, okay? So that's the figure that you're supposed to see in looking at the pictures on the night sky. All right? What gets worse is that if you take these and you draw them out there, we actually, in some of our art, take all the constellations and put them on the celestial sphere. This is an armillary globe at the Woodrow Wilson Memorial in Geneva, Switzerland, and it has all the constellations on a sphere, right, where they are all at the same distance from what would be Earth in the center. And you say, that's just art, right? But no, we actually do it in astronomy class, because in order teaching the night sky and the relationship of the Earth and the sun and sometimes the moon and the stars and everything and the rotation of the night sky, we teach about the celestial sphere. And in this one, we've put all of the stars exactly on the night sky. It can also lead to some really silly things, such as the ceiling of Grand Central Station. Now, how many of you have seen the ceiling in Grand Central Station? All right? How many of you have recognized that it's wrong? The ceiling in Grand Central Station is wrong, okay? We look up here, we see the night sky. Oh, it's got the stars and it's got the constellations drawn in. What they did, however, is they put them up backwards. Orion is fighting Taurus the Bull upper left. On the night sky, Taurus the Bull is upper right of Orion. What happened? They took the constellation figures as they were drawn to be on the outside of a sphere, like that armillary sphere in Geneva, Switzerland, and then they put them on the inside of Grand Central Station. So they got the constellations backwards. Except the person doing it recognized Orion and knew the pattern of Orion and said, wait a minute, look at Orion. Orion looks like this. So notice the belt of Orion is in the correct slant. It's not the way you plotted it at first. It's in the correct slant. They swapped the stars of Orion, even though they didn't swap any other stars. So everything else is backwards except for the constellation of Orion. Because if they were put Orion incorrectly, it would look like this, and you can see the belt would be like this. This is how Johannes Hevelius originally drew it. When I took that Hevelius image, matter of fact, what we've done with all these Hevelius images at the Space Telescope is we've taken his drawings, we've removed all the stars, we have flopped them so that they face normally, and then put them up on the web for planetariums to use on the inside of planetarium domes. If you're trying to use something that was drawn for the outside of the sphere on the inside of the sphere, you have to flop it left, right. Okay? So we want to try and remind people that this is not how it really is. It's not a two-dimensional surface. The stars aren't at the same distance. We can, of course, extend the charting the stars exercise that we did yesterday. So yesterday we had the charting the stars, and we finished with this drawing here. All right, and we had this table here that you utilized. And in this table, you plotted right ascension versus declination, right? But as I said at the end, there's lots more data that you could work with. In particular, we gave you, okay, and so that was one thing. And so I want to draw in the stick figure for you using the Aryan deck thing. But in particular, we gave you the distance column here, right? So that you have the distances to all of these stars. So one of the things we considered asking you to do as an addendum to the charting the stars exercise, but it took long enough yesterday, so we'll just do it in PowerPoint today, is to take the declination and the distance and plot them on a chart like this. Okay? So now we have declination on the y-axis, the same as before. You'll notice I've used the exact same scale here. declination. And now we have distance on the x-axis, and this is in terms of light years, okay? From 0 to 1,500 light years. If I, whoops, go back. All right, if I go back here, you can see the distances range from about 246 for Bellatrix out to 1345 for Alnilam in light years. All right? So if I plot them, I get that. Okay? We get a variety of distances for the stars. It's even more compelling if I draw in the constellation lines. So that's more of the true shape of the Orion constellation, in that it isn't that nice little stick figure that makes the X in 3 dimensions. It looks something like this. All right? But this is only one perspective in 3 dimensions. What I'd really like to be able to do is give you a nice full 3D perspective on it. For that, I've got to get all of the data, all right, and pull it into a format that I can really use. So we're going to go to the Hipparcos star catalog, which is where I got those distances for the stars in Orion. It has a catalog of 118,000 stars. It has the position on the sky, the RA index. It also has a measurement of the parallax. We talked about parallax this morning, the angle that that star moves as Earth goes around its orbit. Okay? It's also got spectral type and magnitude, et cetera, other parameters that you might want to use. The Hipparcos was a satellite designed to measure parallaxes. Right? It was designed to measure parallaxes, and it was, as it went around as it orbited Earth, as it went around the sun, it wanted to have even numbers of stars all across the sky. So it doesn't have quite full sky coverage, not completeness. It has even sky coverage, but not necessarily complete. We're going to add to the Hipparcos catalog the Yale Bright Star catalog with the brightest 10,000 stars. Same information there, but this one is complete, so we make sure we get all of the really bright stars. All of the stars that you might recognize that the human eye could see. All right? Pull those together. So let me illustrate you what stars look like. Now I'm going to start in the visualization aspect of it. So from this image here, I've pulled out a variety of stars. This one's a star of magnitude 5.67, 4.5, 319, and so on, up to the brightest star, which is Sirius, which is really one of the reasons I like to use this image, because that's the brightest star in the night sky. And so I can show you a range from, just barely visible to the human eye up to the brightest star in the night sky. And what you notice is that it goes from a little dot to a bigger dot. And then that bigger dot develops these fuzzy wings around it, okay? All right, and I can model that mathematically by using Gaussian and exponential splats, okay? So a Gaussian profile and an exponential profile gives me the kind of view that I want. So this is a growth of a Gaussian. As you go here and come down here, you can see you get a nice solid core using a Gaussian splat. Using an exponential, you end up getting a very fuzzy splat. It's got a very tight core, but it's got that fuzziness in the wings. By combining a Gaussian profile and an exponential profile, I can model how the stars look in the Akira Fujii image. So my visual model, based upon that image that I showed you, is to take the stars and increase them in magnitude. And you can see how it changes the Gaussian, and then you start adding in the exponential to get those beautiful wings. All right, so I'm mathematically simulating the growth of a light splat in a photograph. Then I need to do colors. And as you've known, the sun is not yellow, it's more white. Matter of fact, as part of all the colors, here are the spectral stellar types in the OBEFGKM table, all right? So what has been done here has been taken the black body curves and gone through the human eye response in order to get the colors with all the various surface temperatures of these various stars, all right, to get the colors along here. And the sun here, these are the RGB in 16-bit hexadecimal notation. Okay? Anybody deal with hexadecimal notation anymore? Oh, it was all the rage back when we were kids, working in early computer stuff. All right. It's all right. It's just a very compact way of representing numbers. Okay. So these are the colors that we've got. So taking those profiles and taking these colors, which all of the stuff that comes out of the Hipparcos catalog, I can take the original image here and I can reproduce it with the Hipparcos catalog over here. And if you do a comparison in terms of Sirius and Betelgeuse and Rigel and such, you can see that there's a lot of background stars that the Hipparcos catalog doesn't have, but we can do a relatively good job of reproducing the stars that the Hipparcos catalog does. So what's the difference? Well, this is a photograph. It is inherently a two-dimensional image, right? I can't take those stars and move those around in 3 dimensions. This comes out of a catalog that has right ascension, declination, and distance. Matter of fact, the brightnesses use the distance in creating of them. So this is fully 3D. All right? So I can then take that, and I don't know why I have the, I can then turn that into a movie. And this movie's not going to play, so I actually have to exit out and go in over here, because I realized last time we did this that, hold on, that the movies, were set up for my Windows machine last year, and I did not transfer them to the new movies for my Mac. So, oh, it doesn't play automatically. There we go, play. All right, so here are the stars on the night sky, and here we're just going to pan across the night sky until we see the Orion constellation here. So taking that data set and the visualization, I can draw in 3 dimensions those connector lines and then start to rotate around the Orion constellation in 3D. You can see how quickly it breaks from the familiar pattern into an elongated pattern. At this point, I have to back the camera up to keep it on screen. This was done in 16:9 aspect ratio, but still we needed to back up the camera. All right. Here you can see all the other stars in the Hipparcos catalog passing in front and behind. Now you will notice Betelgeuse, which was one of the brightest stars, is now getting further and further away from you, so now it is a fainter star. The point is that this visualization is being done scientifically correctly. I will pause it there. Okay. When viewed from the side, it has this really big, long, elongated structure. One kid said, "Oh, I know what that is. That's the stealth bomber constellation." All right. Alnilam, which is the most distant star, now becomes the brightest star. I'll pause it there. Somewhere in Grand Central Station, it's had at a time, I don't know if it's still there, a plaque that says, "Some people think that the constellations on our ceiling are backward, but they're not. They're just viewed from a point outside our solar system, as if you were looking down." Well, this is the view from behind Orion. Does it look like Orion backwards? Of course not, because it's a different 3-dimensional perspective, right? Because the stars are at different distances, you get a different 3-dimensional perspective. If the stars were all at the exact same distance and you go around the back, yeah, they would be backwards. But because they're at all different distances, you can't possibly get it. All right? So here is Betelgeuse, very dim, and Alnilam, very bright, because we're doing a correct 3-dimensional perspective, and the brightnesses of the stars are 1 over r squared dimmed the further away they get. So the ones that are closest will appear brighter. All right? We'll continue our 360-degree spin around it. And so this is the true shape of Orion, right? You may think of it as that familiar X pattern on the sky, but that's the true 3-dimensional shape. When we finish our 360-degree spin, we'll be looking from the direction of the sun, but we backed up earlier on. So let's get back here. All right. So now we're from the direction of the sun, but we are further away than the sun. And even pulling back further away, we still get a little bit of distortion. The one question I want to ask you, where's Sirius? The brightest star in the night sky. Obvious, right? Where is it? Watch carefully as we zoom back in. Come back to the position of the sun, and there. That's where Sirius comes in. Okay? Sirius is the brightest star in the night sky, not because it's an intrinsically really bright star, but because it's actually a medium bright star that happens to be 8 light years away. You put Sirius 10, 20, 30, 40 light years away, and it's no longer anywhere near the brightest star in the night sky. What we see in the night sky is a function of where the stars are, their brightnesses, and where we happen to be relative to those stars. Okay? I always find that to be a fun illustration of that. All right. Break out of full screen mode there. And kill that. All right. Any questions about visualizing those stars? Yeah.
Not a question, but
Sure. Comments, ideas.
one way you can do it, I've seen this done with, I think it might be pretty common, with earthquake foci at subduction zones. Like,
Earthquake foci at subduction zones.
So like they
Okay.
occur at different depths. So it's
Right.
the same problem. You can do from the surface, the epicenters marked as like pins or holes poked in like a piece of paper. And then underneath you can suspend strings of certain distances away.
Right.
You can see how far away they actually view. Like you get the pattern from the front and you can see where they actually are relative to, I don't know.
Okay, so looking down on the Earth. No, so it's a similar thing. Looking down on the Earth, you see the earthquake, the epicenters of the earthquake. But what truly is, it's actually a three-dimensional structure underneath.
Right, you suspend the strings from underneath, so low, shallow foci are suspended by a small string, and it shows the pattern that you view from the side, which represents the subduction, or the friction forming those earthquakes as it, in between the plates.
Cool. All right.
So it might work as a representative way to do that, like within a classroom.
All right. So there have been things called stellariums. There's a company called Stellarium that actually builds models of the stars. And what they do is they take wires and they suspend them from ceiling to floor, and they have a little light bulb on them. Yeah. All right. And so the light, relative to the sun, they put the star up or down and add a brightness onto it to try and give you a three-dimensional view of the stars. I believe there's one at the Smithsonian in Washington, D.C. Has anybody seen one of those in a museum?
You have to look up into it.
Well, actually, it's a case. It's a darkened case because they can't darken the room without it being dangerous. But it's a case that you can walk around and look in through the panels to see the patterns of the stars. But one other way that people have represented it is by doing a visualization with lines up and above and below a plane in terms to indicate where the stars are in the local neighborhood. So you will find some star chart three-dimensional visualizations online that shows a radial polar plane, right? So concentric circles, and then lines above or below that in terms of indicating where the stars are. Okay, so I guess one could do that with the strings and as well in terms of trying to create a box of Orion. That would be interesting, whether or not it's a science project, right? Type thing. View it from this side, you see the constellation Orion. View it from the side. Yeah. Okay. Other thoughts, ideas? Okay, moving on. Let's talk about a smash hit. Okay, so we're going to talk about galaxies, okay? And galaxies are these huge agglomerations of stars and gas and dust, and we talked about them. But galaxies sometimes have companions around them, okay? The Whirlpool galaxy has this very small companion, which might be responsible for the beautiful nature of the spiral pattern, in that the gravity of this can incite resonances that creates this really nice, beautiful spiral pattern. But sometimes, as we discussed earlier, that galaxies are close enough with their sizes compared to their distances that sometimes they can pass right by each other. They can get close to one another. These two galaxies are not actually colliding, they aren't interacting, but these two galaxies are nearby one another. All right? Sometimes we actually see the galaxies in collision, in which they rip each other apart, which they destroy each other's shapes. And so we would like to actually explore this idea of galaxy collisions, but we want to do an exercise with you guys first, okay? So let's pass some of these things out, all right? So you and your partners, however many, how many do we have of these, John?
A lot.
Okay, so
I'm going to start with 4 for each.
4 for each table of 2?
I'm just going to try that.
Okay, so you get 8. All right, I think there's more than that. Because they need more than that in order to try and work things out, right, John?
I think so.
I think they're going to need more than that. We have here a bunch of images of galaxies interacting galaxies. Thank you. Just give me those. All right. There you go. So what do we got? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They should try not to have the same ones, and if they do, trade with the people. All right, we have multiple prints of the same galaxies. Here, have another one. Here, have another one. All right, so if you look through your set of 4 or 5 and you have multiples, go ahead and trade with your neighbors. All right, so what we would like you to do here is...
Do you need something to show with?
Yes, that's it. All right, so you have here multiple galaxies interaction, all right? So what we would like you to do is try to develop your own mental model of how galaxies collide. So we want you to take a look at some galaxies and say, well, where are 2 galaxies that look like they're just beginning to come together? All right? Where in the stage of a galaxy collision is each one of these images? If we have 2 galaxies, what about these 2 galaxies? Okay, I'm just going to grab a random one here. All right, these look like they're well separated. Could these be early in the collision? Could it be midway through the collision? Could it be late in the collision? You remember those little puzzles when they would say, all right, here are 5 pictures, place them in time sequence. We want you to try to do that with these galaxy collision images. All right, so take a look at the galaxy collision images we've given you. Try to identify which might have occurred before the other. All right, they are separate, they're different galaxy pairs, but which one represents an early stage of a collision, middle stage of a collision, late stage of a collision, okay? So we'll give you a few minutes to try to play with that. How many of you guys? All right, so who would like to share with me a galaxy pair that is early stage? What did you guys choose for one that's early stage?
One that had a lot of blue.
Okay.
And spread apart.
All right, so hold on, let me show you. This is their choice for an early stage. Okay, and because, what are the reasons?
Because it had newer stars.
Because it's, you said blue, so young stars. Okay, so we've got lots of blue stars, and
Spread apart.
they're far apart. Okay, so early stage, they'd be on approach, they might be far apart there, okay? All right. Who else would like to show me an early stage? How about you guys? What do you think for an early stage? They had the same one. Okay, cool.
But
All
the
right.
reason we associated that was
All right, what other reason?
their structure seemed to be well defined. There wasn't a lot of distortion. They seemed relatively spiral in both cases.
Okay, did you guys hear that? There's too much mumbling in this room. All right, he said a very good comment there, that the distortion is minimal, that they had the spiral structure we expect of spiral galaxies. All right, nice comment. All right, one more from you guys over here. What's an early stage one from you? All right. All right, IC 2810, they said. Okay, so this is their choice for an early stage one. What's the reasoning behind it?
Wait, come back here one more time.
Oops, there you go.
Apart, kind of like the others, and they also have the definition of a spiral.
Okay, so things that were far apart on the page, all right, and still look like normal galaxies. All right, I'll accept that. Okay, group in the back. I was going to ask for a later in the stage. Okay, so we've done our early stages ones. What about a mid stage one, or a little bit further down the line?
Those two are just starting to touch.
Okay, so here they've got one here. What is it? NGC 6090, one of my favorites. I have no idea who would. On NGC 6090, they said that the two galaxies are just beginning to touch, what they can see. It's actually kind of small in here, so hard to hold up and work around. How about you guys over here? What's another mid-stage one? Okay, here we go. NGC 3690, over here, everybody. This is their choice for a mid-stage one. Why would it be mid-stage?
That they're beginning to interact.
Okay, they're beginning to interact. Looks like they're just starting to touch and starting to go through. All right? Okay. I need a third mid-stage one. You guys want to think? Oh, they want to have. Oh, here we go. Here's a nice one. NGC 6050. All right, take a look at that. Reasons? All right, so what's the reasons for this?
They're starting to touch.
They look like they're starting to touch, but they still have their spiral structure, okay? So we're getting the ideas that they're going to start off with their nice normal galaxy structure, and as they approach and start to touch, you know, something's going to happen. All right, let's go a little bit further. Up in the front corner, what's one that's further than that? So we've got it approaching and starting to touch. Give me something a little further than that. Okay? So ESO 77-14. Okay, so you can see the two galaxies here, and you can see some what we call tidal tails along there. All right, did you know they were called tidal tails? That's what they're called. Okay, everyone can see that. Tell us why you think these guys, what's happening here?
They're in between them. It looks like they're sort of pulling toward one another, but looks like they might have even kind of already passed through one another.
Okay, so you notice the bridge of material in between them. All right, that's kind of hard to see unless you look at it up close. ESO 7714, that there's a bridge of material between them. All right, so they could be
like a trailing.
Could be something that's being pulled out of each other or something, or.
Once they get close enough, they start to pull, it'll like fuse.
All right, so they get close enough, and the gravity pulls stuff off of each other. Okay, yes.
Could they be in the beginning stages though, too?
That's what he was saying. He wasn't sure.
That's
Right.
We had it in the beginning stages because we had the same one, just because it looks like they're still separated. They still have some of the swirly features of it, and they are kind of getting closer towards each other.
Okay, cool. All right. So it's hard to tell by looking at the galaxies, have they passed by each other or are they on approach, okay? I mean, if two things come in like this and go like that, how do you know that they're here or that they're there, right? Good answer, good ideas. Okay, how?
Were we not
Yes.
supposed to assume that they were all going to collide? Because I figured this was a...
Yes, all of these galaxies are interacting, and all of these galaxy pairs will end up merging together as a single galaxy at the end of it, okay? But we're just seeing the different stages of it here and trying to, can we visually identify those stages?
Yeah, we didn't realize that's what initially.
Okay?
But will any of them pass? Like, none of the ones you show us will actually pass by each other, and they'll all collide.
All of the galaxy interactions we show you here, these two galaxies are actually going to collide, yes, okay? They may pass by each other once and then come back in the process of collision, because collisions can go multiple different ways. Uh-oh, thunderstorm coming. Our flash flood watch. All right, so why don't you guys take us one step further? What's something where you definitely see it colliding or something? Ah, NGC 6240. All right, so here's 6240. If everyone can take a look at that. All right, what did you think? Tell us what you think about this one.
It looks like a Star Wars explosion.
It looks like a Star Wars explosion. Okay, you realize that was the original Star Wars explosion when they exploded the Death Star. They put the camera on the floor and they put the Death Star up here, and they did explosion here so that everything would come out circular and it would look like an explosion in space. Because if they film it from the side, gravity is going to show it. So by putting the camera on the floor, it made it look like it was an explosion in zero gravity. Silly trivia that I happen to know. Okay, so it looks like things are exploding all over the place. Okay? All right, did anybody else have 6240? Yes, what do you guys think of it?
We thought the same thing.
Thought the same thing. Stuff is going all directions, okay? Who else has got one where you definitely feel like there's some collision? What have you got going on over here?
ESO 148-2.
ESO 148-2. Don't you love these galaxies names? I'm sorry, most of them aren't called Fred. So here is ESO 148-2, okay? And you've got a clump in the center, and you've got some tails heading north and south. What's your comment on it?
We figured they had just collided probably, or were in the process of that because of the two different tails. Obviously there were two different ones, but they'll make one mass in the center.
Excellent deduction that you see the two tails. Obviously there had to be two entities involved in it, even though you look at this and it looks like there's only one object in there. Okay? Cool. Cool reasoning. All right, who else hasn't think? Ladies over here who had a really cool, really funny story that they're not going to tell the rest of us. Take us, so collision, further, aftermath, what do you want to show us? Which one do you like?
They both look like the collisions. Just
All right,
because of
I'll
the
hold up
tails
both.
that we talked about, kind of like a crisscross effect with the two.
Okay, so these are two, these are two ESO phone number galaxies. All right, and so you say there's a crisscross effect of the various galaxy structures making an X shape? Is that what I'm saying? That I'm hearing?
Yeah, you
Okay.
see the two distinct ones, but they're together.
Okay. All right. Anybody else have one that they would like to hold up and say what you deduce is going on there? I think I've talked to everybody, right? Every pair has had something to say. All right. Did I get you guys?
No.
I didn't get you guys. Okay.
I think this is the one that maybe just collided. It looks like a hamburger.
UGC 5101. You said it looks like the Hindenburg?
No. Hamburger.
Hamburger, okay. She says it looks like a hamburger. No, and that's not silly, right? Let me tell you truthfully, there is an object in the universe that astronomers have nicknamed Gomez's hamburger, okay? Because it's got two all beef patties. No, because it has a bright thing above it, a dark dust lane in the middle, and a bright thing below it, which gives you the hamburger look, right? So that brown dust lane in the center can be the hamburger patty in between the two bright, bright gas buns, okay? Just the way, okay? This isn't Gomez's hamburger, this is a galactic hamburger. Okay, all right, cool. So is the purpose of this for you guys to know exactly what's going on here? All right, no, the purpose of this is for you to start to develop a mental model of a process that you have no real familiarity with, okay? If I ask you to imagine two galaxies colliding, right, and I didn't give you these pictures, you might come up with a very interesting model in your head of how they collide. By giving you the pictures, you can actually start to see there are some things where, all right, well, these two galaxies are pretty far apart, so I don't think they've really started their collision, but these two galaxies, they look like they've sort of combined into one, but you can see the tails, so this must be later in the process. All right, so we as astronomers can't do any better because a total galaxy collision takes 1 billion years to happen, right? We can't follow two individual galaxies over the course of 1 billion years. Yes?
I have a question about the motion. Do they ever, all of ours seem to So do galaxies ever move toward one another like face to face, or do the way galaxies move through the universe like generally in the direction of their plane?
There should be no preferred orientation for a galaxy's bulk motion through the universe versus its orientation, but I can imagine in clusters of galaxies there being some correlation in the orientation. A lot of these collisions will happen in clusters of galaxies where the density of galaxies is higher. So there can be a little bit of orientation within clusters, alignment of things, but in general, there should be no correlation between their motion, their bulk motion, and their internal motions. Yes?
This could be a silly question, but can two galaxies go through each other with almost no consequence, or is there always something being pulled?
Excellent question.
Still your time.
He's setting me up. All right, so what did we learn about stars this morning? Our baseball analogy, right? There's tons of room between two baseballs for other baseballs to pass through. So when galaxies collide, are the baseballs within them going to collide? No. The stars are going to pass right through each other because there's so much space on average between stars that the stars are almost never going to collide. When the galaxies collide, the stars will stream through, but what is going to collide? The dust and the gas, the clouds, the nebulae. All right, all those gaseous structures have to collide. They take up real volume. All right, they will collide, they will shock heat, they will do their collapsing, they will cause star formation and such. But it's actually the stars themselves that sort of free stream through it. So yes, that's later on in my talk, but that's a cool thing to talk about because it came up. Because that's one of the reasons for doing this and setting you up with the baseballs in the morning. Okay, so let's talk about some galaxy collisions and how we would represent these things. All right, in astronomy, in order to watch a galaxy collision, we have to create it ourselves on the computer. We need to do some computer simulations that are based on particles. You don't need to know the details, but you do need to know that we represent both the stars as points, relatively small points, as well as the gas clouds as a cloud with a density profile. Okay? That's all you need to know, because when we present it in our scientific papers, this is from the Astrophysical Journal, you can see we do it in a way that, again, only astronomers could love. All right? Not terribly beautiful and exciting. If I take that data, I put it into a visualization program, I can make it a little more exciting, right? However, what I'm doing here is I'm representing all of the particles in the simulation as individual points. And I just got through telling you that we really don't represent them as points. In the computer model, they're actually clouds, right? And I need to represent them visually as clouds instead of representing them visually as points. So we go through and actually, we use a Gaussian splat because the Gaussian splat can almost exactly represent the 2D projection of the 3D density profile. So if I take the 3D density profile, I compress it onto a plane, and then I model it mathematically, I actually get this line here, and the boxes of the Gaussian almost perfectly can be scaled to match what the spline is. So I can match visually what is going on in the computer simulation. And it's really important to do so because when you do that, you go from these points here, all right, down to actually seeing the details of the galaxy. All right? Brandon, would you do me a favor and turn off the extra lights because I'm going down into these things? Okay. Yes, you can wait. Bonnie's pictures can wait. The one on the left, all the way to the left. Thank you very much. All right. So now you can see the detail that this is the exact same simulation, but visualized two different ways. Instead of doing points, we actually do the cloud splats. We see all the structure that's really there in the simulation. It also shows up in the stars, even though the stars, because the stars are modeled still as tiny, tiny, tiny clouds, but they still have some cloud structure that you can see with the two different visualizations. All right? Add them together, you can get these two galaxies approaching each other before they've collided, and then they smash together and rip each other apart and develop these big, long tidal tails. I can show you this movie, but I want to take you one step further because I really don't want you just to see the galaxy collision. I want you to understand how Hubble and how the Hubble telescope and astronomers in general view these galaxy collisions, because the images that you just looked at were part of our largest press release ever, 59 galaxy collision images, or interacting galaxies. Some of them aren't actually colliding just yet. And you can see that we had 59 different one of these, 37 of which I passed around for you guys to play with. And I did this process, exactly what you just did here. I did this process, broke it down, looked at them and said, okay, well, which ones look like they're approaching? They still have their spiral structure. All right, this one is one that I used for approaching. Here's one where it looks like they're just slicing through each other, and so on and so forth. I pulled them out, and I said, okay, what's early, middle, and late in the process of the galaxy collision? We separated them out actually into a bunch of different piles and chose, the ones that were, really beautiful from each to try and see if I could do the visualization. I then went back to that computer simulation that I had already previously done with the yellow and blue, and I tried to find, okay, where in the stage of this computer simulation are the galaxies at roughly the same stage as they are in the images from Hubble? So I found those stages, and then I had to then position the camera, which is not as easy as it sounds like. You have to really, we had to develop some interactive routines so that we could position the camera so it roughly matches the view of Hubble when it saw those images. Taking all those together, then I had to revisualize it to sort of match the brownish color palette of these images. So we now take it to the brown, and then I've got a visualization that can show you not only the galaxy collision, but also how astronomers observe it. So this visualization, which won't play again, all right? So I have to go to here. Where's my mouse? There it is. I call galaxy collisions simulation versus observation. There it is, right there. And I have to bring it over onto the screen. Oops. Okay. So galaxy collision, simulation versus observation. Here is the simulation. But if we pause it there, we can crossfade to the Hubble image. All right? Shows you two galaxies at roughly the same stage. Same simulation, turn it on. One galaxy just goes slicing through the other. All right? You notice how they keep most of their spiral structure up until they collide. All right? When viewed from this angle, it matches this Hubble image. Very quickly after they collide, they develop those tidal tails. So those tidal tails are signatures of actually having had an interaction, as we see in this Hubble image. All right? And then you saw that bridge, right? You guys mentioned, well, that bridge, that's material flowing back together as those two centers where all the mass is knows where it is. You view it from a skew angle like this, and you see what we see in this Hubble image, where you get the tidal tails spewing around. And then those two centers are going to merge together because that's where the mass is concentrated. That's the inevitable result of all of these things. And when viewed from the side, it's a train wreck, all right, where we got the two galaxies in here and the tidal tails coming out. Although in this case, it's actually got this big, long S shape in the process. It will take, that's about 1 billion years of a galaxy collision, and it will take about 1 billion years more for that to happen, all right? So the idea, and this has become one of my most famous visualizations because it's used in Astronomy 101 classes all over the place, is that you get to see the computer simulation and you get to see how the stages in it relate to the Hubble images. And that each Hubble image is just one snapshot in a movie that lasts 1 billion years. That we astronomers can't ever see one pair of galaxies collide. We can't ever watch the entire collision. But by looking at various other galaxy collisions in a statistical sense, we can get a feel for it, and that supercomputers are powerful enough to take millions of particles, run them through the equations of gravity and hydrodynamics, and smash them together to get us a realistic representation of a galaxy collision. I have to say that when I showed this visualization to Lars Hernquist, one of the astronomers behind the computer simulation, he said to me, "Damn, I might actually believe my simulations now." Because all of our computer simulations are just that, simulations, but you can see how well, at least in this case, they relate to reality. All right. Oops. Escape out of that. How do I? All right, I want to take this one step further because in our case, this is actually going to be of relevance to us in a little while. Because this is our Milky Way galaxy here. We see the plane of our Milky Way galaxy here, the nice thin disk of it. There's an object right there that we need to worry about. That is the Andromeda galaxy. And we talked about cosmological redshift, right? Well, this doesn't have a redshift. It's too close. Matter of fact, it's got a Doppler blue shift. All right? The Andromeda galaxy is headed towards us. And we have known this for 100 years, that the Andromeda galaxy is on a path towards us. But what we haven't known is it going to collide? Simply because we can measure its radial velocity, but we can't measure its sideways velocity. And the Hubble telescope was the first one to be able to measure that sideways velocity. This is just showing you that it's got a Doppler blue shift. Okay, are we going to collide? So in the velocity components, all right, your vector stuff, if you teach vectors, we have a radial component, which is away from Earth, and a transverse component. Doppler shift only measures the radial velocity. It does not tell us anything about the transverse component of it, okay? So that vector is unknown, all right? The way we measure transverse velocity is something called proper motion. And that's actually by watching things move across the sky relative to stuff that's not moving. This is the largest proper motion of any star. It is Barnard's star that I mentioned the other day, okay? It's got a 10.3 arc second per year, but it's only 6 light years away, so that's the reason why it can have a very large proper motion across the sky. It's got a big, large sideways motion. If M31 has a typical sideways velocity of maybe 100 kilometers per second, but it's 2.5 million light years away, then it would only have a proper motion of 30 micro arc seconds per year. All right, that's kind of hard to measure, right? And the thing is, the folks doing Hubble actually figured out how to measure it. It's an amazing technique to measure at micro arc second accuracy. So this is the first proper motion measurements for galaxy M31. What they did was you have a screen of things. Well, you have the foreground stars, which we don't really care about. We have the stars that are in Andromeda. We're looking in the halo of Andromeda, and we have all these background stars that we need to measure. We have all these background galaxies in the background that we can measure against. Remember when I talked about positional astronomy on the sky? It's easier to measure differential, this distance between here and here, than absolute. Here again, we've got all these background galaxies to serve as a rest frame, and it's easier to measure differential against those than it is to measure any absolute motion. So over the course of 5 to 7 years using this and using basically what's called subpixel analysis, we didn't actually have to see the brightest spot move an entire pixel. It could move just a little bit, because if you model that point spread function here enough, if it moves just a little bit, well, then all of the surrounding pixels will change by just a little bit. So some of the pixels will go down, some of the pixels will go up. And by doing that subpixel measurement, which had not been done before, they were able to measure the motion down to, what was it? Thousandths of a pixel. So the Milky Way, the Andromeda galaxy is on its way towards us. They got to tens of micro arc seconds per year is what they measured. All right. The transverse velocity relative to our sun was 140 kilometers per second, about what we had estimated it might be. However, the important thing is not relative to the sun, that's heliocentric, it's galactocentric, measuring relative to our galaxy. So you transform from the rest frame of the sun to the rest frame of the galaxy. What do you get? Well, the radial velocity is that 100 kilometers a second, but the transverse velocity is 17 plus or minus 34 kilometers per second, which is consistent with 0 transverse velocity. The Andromeda galaxy is consistent with a head-on collision. All right. So of course, when we do a press release like that, we've got to go do a visualization of it. So where is it? MW. There we go. All right, so here is the visualization of what's going to happen in our future. In our future, we have the Milky Way galaxy. Why is that not full screened correctly? Hold on. There we go. Okay, so there's our Milky Way galaxy. It's doing its thing, and then the camera pulls back to expose the collision in progress. Here's Andromeda and our Triangulum galaxy. The camera is going to pan around and you're going to see just how thin the Andromeda galaxy is when you look at these edge-on disks, right? Again, this is a computer simulation, not any real data. But in about 3.9 billion years, are going to come smashing through one another. All right, you can see the tidal tails get developed. The two centers of the galaxy will go apart. But as we know, they will come back together, smash, and fly through each other and mix. And about 5.5 billion years from now, they will become one galaxy. The Milky Way and Andromeda will join together. Well, in this version of it, M33 just sort of floats around the outside, watching the whole collision. Okay? There are some versions of the simulation when they change the parameters in which M33 actually becomes involved in it, and we get all three of the major galaxies in the local group merging together to become one galaxy. So if you like our Milky Way and you really enjoy taking a look at it, it will be there for another 3 billion years. About 4 billion years from now, we're going to be part of the Milky Way. Milky Way and Andromeda will merge together. Yes?
So I have a question. At what stage of the collision would planet Earth start to feel some effects from it?
Always the question we get at. What's going to happen to us, okay?
At what stage would we start to, or our planet would change? Or
Okay. So we're in the sun, and the sun is the sun is halfway out inside the Milky Way galaxy, right? So we are going to be tied to the sun, and as you know, there's a lot of distance between the sun and the next star. That even an entire galaxy passing through us, we will not be dislodged from the sun. Okay, Earth will stay with the sun and will continue to orbit the sun. But watch what happens when the two galaxies collide. You will see a lot of stars are going to get flung off onto very large orbits, thrown way out here. Okay. Or they get dropped into very small orbits and orbit in close to the center. Those are the two most likely scenarios. The most likely scenario is we get thrown way the hell out of the Milky Way galaxy, and we're on this big plunging orbit, and we go zoom through, and we go zooming through. So instead of that nice circular orbit around the center, we're on this big elliptical plunging orbit. All right, and our view of the galaxy changes over the course of hundreds of millions of years. But we will not get dislodged from the sun, okay? So we'll still be with the sun, but we'll be on this plunging orbit. Of course, as we discussed the other day, the sun's going to heat up, and by this time it's going to be too hot on Earth to actually have life here. So we'll have other things to worry about at this time too, okay? So about the same time that we're going to lose the ability to have life on Earth, we're also going to be smashing into Andromeda. Yes?
Did we find that the amount of material in a standalone galaxy is a lot more than galaxies in clusters?
Not really. Are you talking about dark matter?
No, I'm just saying, like, if our most
Okay.
By themselves, is that one's a cluster that now that some of them are pulled together, so they're just further along in that phase, which means they might have more material?
Well, the amount of material that's in a standalone galaxy, including all the dark matter and the gas halo around it, if you put that into a cluster, well, then some of that gas halo becomes part of the cluster material, right? On Monday, I showed you an X-ray image of a cluster of galaxies, and there was all this hot gas. Well, all that extra gas that's around the individual galaxies merges to become a communal halo that glows in X-rays. So, in as much as the mass is still there, but it's not uniquely associated with any galaxy, right? So the clusters of galaxies are agglomerations of individual galaxies, and then a little bit more material that flows in. So there would be, on average, more mass per galaxy in a cluster because it's a greater gravitational entity which attracts more stuff from around it. But each individual galaxy sort of brings in its own helping of mass and stuff.
Suggesting maybe like a standalone galaxy might be larger than galaxies and clusters because they were once a cluster and they pulled together.
Oh, so you're saying if like in 5 billion years, when Milky Way and Andromeda have collided, they will be a double-sized galaxy, right?
Yeah.
Right. So elliptical galaxies, which we believe are the result of mergers, are larger in mass than spiral galaxies, which we do not believe are the results of merger. So yes, merged galaxies are bigger, right? Because you're taking the mass of two galaxies, smashing them together, and you could take 3 and 4 and 5 galaxies. So the largest galaxies in the universe are these giant elliptical galaxies, which actually occur at the centers of clusters, where you've had several galaxies merge into becoming one galaxy at the center of the cluster.
So do clusters represent sort of a young phenomenon, or are they sort of an aging one because they're soon going to have an elliptical galaxy at their center?
Well, a cluster without an elliptical galaxy at its center is a young cluster, I would say. But a cluster with a huge elliptical galaxy, you could sort of say is an older cluster because it must have started its clustering earlier.
And standalone spirals are youngest?
Standalone spirals, they can be young or old because, yeah, how do you age date a spiral? You know, they just have remarkably good, they age very well. They also dye their hair, you know. Okay? Yeah, cool. All right, it's time to take a break.